testing. This guy works much better. So thank you very much for coming out here to enjoy this lunch and hopefully this talk. So today I'll be talking about detection of milk protein adulterants. It's a very important problem, mostly in developing nations. Specifically, it's a big problem in China and India. But before I start, I just wanted to get a show of hands of sort of what the audience is like. And I was wondering how many folks are working in any sort of chemical sensing or have worked in chemical sensing? Quite a bit of you. And sensing for healthcare? So many of you are familiar with some of the issues involved with this. So anyway, without further ado, I'll sort of describe what's going on. So milk adulteration is a very prevalent problem. In 2008 alone, about 1/3 of folks got sick from consuming milk and milk products that have been adulterated with melamine. In India, the Indian authority, which is basically equivalent to our FDA here in the States, estimated in 2012 that, depending on the region, but up to 70% of the milk that is consumed is adulterated in some way or another. And it is very difficult to say how, in other places where they do not have strong regulatory bodies, how much of this food is actually being adulterated. And so you have to understand why these folks adulterate this to be able to go after and identify this problem. So what happens is these folks, they're not trying to kill people. It's one of the things you have to understand, they're not trying to kill people. What they're trying to do is make a little bit more money out of the actual milk that they have. So they usually have some milk that, say they have a liter of milk, and they decide, well, they can make a little bit more money by diluting it. But when the farmer or whoever does this, usually a collection of farmers or some sort of organization does this, they go and to give this milk to a plant that collects this, they check for the nitrogen content in the milk. This way they determine how good your milk is. The nitrogen content serves as basically a mimic for how much protein there is in the milk, and so the milk's nutritional value. So if the milk is just plainly diluted with water, they'll quickly find out because the nitrogen level in their milk is going to be low. So what they do is they find some cheap chemical, usually plastic chemical stalks, or some other fertilizer, some other widely available, relatively inexpensive chemical that per cost of the chemical has a lot of nitrogens in it. And melamine happens to be a good one because it's both widely available. You hear about melamine plastics, melamine maybe tableware, for example, and it has quite a bit of nitrogen. So it's a perfect example for it. So then they add this up. The nitrogen now level is back where it's supposed to be, but now this milk contains these chemicals, and while these chemicals typically do not kill you outright, they have very low lethal doses, but they will contribute to long-term health effects. So for example, the infants that typically consume milk, right, this milk is almost primary source of nutrition for infants and small children. These infants develop kidney disease and will have health problems for the rest of their lives because of this. So detecting this is quite a serious problem. So how is it currently done? People are certainly not turning a blind eye on this. People are certainly trying to do milk detection. So right now, it's done in centralized labs, and typically the two equipment that's used for this is gas chromatography, mass spectrometry, and high-pressure liquid chromatography, mass spectrometry. So these are typical laboratory installations. What you find in these milk processing labs, something not too different from this, but of course they might have an auto-sampler and some automation to put around this. But despite this, all of this involves shipping the sample to these centralized laboratories. And because you're shipping the samples to the centralized laboratories, oftentimes there's delays, and that introduces storage costs, and that introduces spoilage, and oftentimes basically decisions are made without any information. They just decide, oh, I trust this farmer or this conglomerate of farmers, and so I'll take their milk without any question. So it's quite a bit of a problem. And because of this, these laboratories are all, in addition to this, are quite a bit overrun with the amount of work they have, which also introduces problems into detection. So what we're trying to do is that instead of going the traditional mass spec route to form a detector, we're trying to use surface-enhanced Raman spectroscopy to do the detection of these molecules. And so, what is surface-enhanced Raman spectroscopy? And first of all, what is Raman spectroscopy? So, Raman spectroscopy is a vibrational spectroscopy technique where, say, if you have a molecule, melamine, so if you have melamine, this video plays, you'd see vibrations in these bonds. So these bonds, typically in a molecule, they vibrate. And so in those modes, you can store some energy. And so if you shine some light at this molecule, majority of the photons that do interact with the molecule will be just scattered. So they will go up into these, from the vibrational states, they will go into these virtual energy states of the molecule and just come down. And whatever energy you put in is the same energy that comes out. And in terms of wavelengths, this would mean whatever wavelength you put in is the same wavelength of light that will come out. This is the overwhelming majority of the light that actually does interact with the molecule. There's also some absorption. So basically you bump one vibrational energy state to another, so you feed some energy to the molecule. But rarely, but once in a while, you have this very interesting effect where you go into these high energy states, and once you come out, you lose some of the energy to the molecule. And so, say if you feed energy of a laser at one frequency, and you detect energy of another frequency, you can tell what kind of energy states are there in the molecule. Because those correspond to the energy states that the molecule can basically steal the energy from your incident laser beam. And that tells you the identity of the molecule. The nice part about this is that this makes this technique very specific to the molecules of interest. So you can differentiate those molecules from everything else that's potentially can be there. What's bad about this, because this event is so rare, you need a lot of the molecule to be there, or a lot of the laser light, and to some degree that laser light will start degrading things. You can't have increased laser light infinitely. But, therefore, you need to somehow increase this effect. And one way of increasing this effect is through using surfaces. So there's a technique called surface-enhanced Raman spectroscopy, or Raman scattering. And in surface-enhanced Raman scattering, you typically use nanoparticles. And majority of the folks, if you are familiar with SIRS, you're probably familiar with a nanoparticle-based SIRS. So typically, this is on the order of a few hundred microns, maybe the smallest of tens of microns to a few hundreds of, nanometers. A few hundred nanometers, so tens of nanometers to a few hundreds of nanometers. And when they come together, they form these zones of high electric field. And so what happens here is that when you shine energy with your laser, so you have your electric field oscillations, they induce oscillations at the surface of your material. So typically it's gold or silver. What determines the correct material to use is this plasmonic response, or response of these electrons at the surface of the material, so this plasma. So this amplifies the electric field. The molecule that's absorbed to this interacts with this electric field, and so steals some of this energy, and so the electric field now is slightly different, and so the electric field that's being emitted to your spectrometer is slightly different. It's typically because you eat some of the energy, the electric field that's emitted is at longer wavelengths. And so now you're able to capture much more, significantly more photons than you would just probing this molecule with a laser alone. And so how much more? So on this side, this part amplifies electric field by square, so it scales electric field square, and this scales the amplification of the field square as well. And so together, it's an e to the fourth effect. So if you're able to use some of these structures, these nanostructures, to say increase the field, I don't know, 10 to the 2 power, the 100-fold. So now, because now it's electric field to the 4th power, it's like you increased it 10 to the 8th fold, right? So significant, huge increases that you can gain by doing this effect, and that offsets the rarity of the typical Raman response. Okay. So, so typically people use particles to generate these surfaces onto which these molecules absorb and serve basically as an antenna to this laser, to capture this laser radiation and then re-radiate it out. So the problem with using particles, as you can see in this image, when the particles come together to form these regions, especially of high intense electric fields, at these sharp contact points, these contact points are very, very irregular. So here, for example, there is no contact. Here it's a very sharp contact. They kind of squish together. Some contacts are very different. So your enhancement in field is very different, and it forms some sort of distribution. And also depending on the chemical composition of the solution in which these particles were, so also depending on in which this molecule came from, it changes how these particles come together and bind together, and so changes this enhancement. And so it's very difficult to make this quantitative. It's very hard. And so what you can do to overcome this, and what we have done in HP Labs, is form these nanoparticles on arrays of pillars, which we call nanofingers. And when you close these fingers, all of these are fairly uniform, and the gaps are very uniform, and so the enhancement is uniform, and you can make this technique much more quantitative. Because now the distribution of enhancement is not sort of random and Gaussian. The distribution of enhancement is supposed to be more flat, and hopefully flat and also high. Okay? And so what we do is we use nanoimprint lithography, for those who are familiar with this technique. For those who are not, basically this is stamping. It's just a nano version of stamping. You have a stamp that has some pattern etched into it, and you have some resin that you press into that stamp, and once you pull out the resin, and once you cure the resin in the stamp and pull it out, you have some profile. For example, a profile of these nanopillars. And then once you deposit some gold onto these pillars, you get these nice nanoparticles, very uniform nanoparticles on top of these pillars. So this way, you can create very regular nanostructures where you would have to normally rely on randomness and chance. So how do these structures work? Well, you have, for example, if you take this pentamer group, you would immerse it in solution of this compound, And the compound, especially because it's nitrogenous, these nitrogen groups, especially these primary amine groups, have very high affinity to the gold. They would bind to these gold caps onto this molecule, and the remaining liquid will form this meniscus in between these particles, these pillars. Okay? Once you dry the solution, these meniscuses will dry, and by this meniscus will pull the fingers together closed by the surface tension of the liquid that this compound was in. And so once it's closed, these regions form regular, fairly irregular regions of what are called termed hotspots, or regions of enhanced electric field. And so there they can excite the electric field that you saw earlier and act as an antenna to enhance the Raman signal. Okay? And so here you see the SCMs of opened fingers, and here you see the SCM of closed fingers. And if you notice how regular this structure is and these points of contact. And so here is just a blown up version of this SCM where you have this regular structure, and that's a simulation of the electric field. So this represents the enhancement of the field at these points, sort of the maximum of this field, over the background field in R. So by doing an enhancement of order of 100-fold, because now it's amplification of electric field squared on the incoming incident light and outgoing incident light, you can have very significant total enhancements in the Raman signal. Okay. And so now I'll sort of turn that to what you do with a practical sample. So it turns out if you just you have this nice sensor, you have this nice enhancement, very regular, very nice, but you take the sensor and you dip it into a real sample, for example, milk, a very common sample, but however, more or less complex biologically, and so it would be a real biological sample. So, for example, here's melamine, the main culprit in milk adulteration, and here's spectra where you just put it in milk. So you see that there are some peaks, but it's nothing like melamine in the ionized water, right? You see you're missing most of the characteristic peaks, and you cannot discern if it's melamine or if it's just the background. So if I take the milk sample, I haven't plotted it here, but it's very difficult to distinguish the milk spectra without anything and the milk with melamine in it. And so this indicates that we have to do something. We have to purify out this melamine. And for folks who do chemical sensing, this should not come as any surprise. Most of the instruments that we should do chemical sensing, there is almost always a separation and a purification step. For example, in the gas chromatography and mass spec, your mass spec would be the sensor, but the gas chromatography would be the separation component. In HPLC, same thing. The HPLC serves as a separation, and the GC serves as, as the mass spec serves again as a detector. So for this detector, we have to also do some separation. So we hypothesized that milk proteins are the things that are blocking the surface, and therefore are blocking the milk signal. And so we have some data to indicate that is true. As you know, sort of here's a table of the composition of milks. And as you know, majority of milk is actually protein. So it's protein, fat, and some sugar, milk, sugar, lactose. And if we take the milk protein, which is overwhelmingly casein protein, and we place it into a solution with melamine in it, and we take the Raman spectra of this, or rather surface spectra of it, you will not be able to tell a solution that contains melamine from a solution that just contains casein just by itself, right? And here's the spectra of melamine just for reference. And so to remove this, we developed a fairly simple technique, which is highly amenable to microfluidic automation. And this is so the microfluidic automation is what we're trying to do next. But to prepare for that, we wanted to have something that's very microfluidically amenable. Here we use very simple techniques. This can be used in the field. Without microfluidics, you just have to have a technician that will be running this. So here we have a syringe that's filled with a precipitation solution. This happens to be trichloroacetic acid. We have just a regular syringe filter, which is just a membrane filter, and another solution to adjust the pH back up to closer to neutral pH. So with this technique, we just take a cup of milk, and in this syringe that's pre-filled with precipitation solution, we draw up the milk into the syringe. The milk forms this precipitate, and there's also interesting mixing phenomenon that occurs as the milk hits the precipitation solution. But as you can see, it forms it quickly, and it forms it in a well-mixed state, so most of the precipitate occurs everywhere and right away. And then we take that and we push it through just a simple filter. And by pushing it through a simple filter into this pH adjustment solution, we're able to leave most of the milk solids, so the proteins and potentially the fats behind, and just recover the supernatant, which will contain your molecules of interest, the small molecules. Okay? And so then into the solution we drop our sensor, which looks like this. So on this little dot is where your little nanofingers are that you saw on the SEMs. There is about several 100,000 of these little nanofinger groups here. You drop into the sensor, you incubate it, and you wash the sensor, and then you put it directly on a Raman spectrometer. And there's a number of portable Raman spectrometers that are out there. Some, the smallest that we have is about the size, slightly, the volume of this, slightly different format, but about the volume of this little case. And commercially available, there are instruments about this big, so you can put this directly onto one of those systems and perform this analysis right in the field. And so the nice part about this sample preparation is that it only takes about 3 minutes. It only involves about 5 steps, or 4 or 5 steps, depending on how you want to look at it. And it uses very inexpensive reagents and materials. And furthermore, now we're working on making a little microfluidic cartridge to automate this so that you don't even need a technician to perform these few manual steps, so that to eliminate the error out of this, and you can give it to untrained people. So what does this sample preparation give you? So here is a plot of Raman intensity for melamine, and here's, as usual, the Raman shift, and for several different conditions. So here, in the black curve, I plot the melamine, 1 millimolar melamine, in deionized water, so there is no sample, and there's also no sample prep. So here is the positive control and how the spectrum should look like. Here at the bottom, I plot our negative control, which is 1 millimolar melamine in the milk, but again, there is no sample prep. And just as you saw in a few slides back, the spectra here is very hard to pick out any characteristic peaks in the spectra for melamine. Here's another negative control where you have milk, that has undergone sample preparation. And even though this has undergone sample preparation, this spectrum and this spectrum in this relevant region, it's very, very hard to distinguish and pick out any relevant features. Okay? And here now is our actual test cases. This is 1 millimolar melamine in milk that has undergone this sample preparation process where we remove the proteins. This is the same with 0.1 millimolar and one more order of magnitude lower at 0.01 millimolar. And you can see that we are able to clearly distinguish all the relevant features of the spectrum. And the peaks all in the spectrum correspond and agree relatively well with those numerically predicted for melamine. And so using this sample preparation technique, we're able to directly detect melamine from milk, from whole milk, and so from a realistic sample in a fairly short time, allowing to do this in a portable manner. And so you might ask, well, are these concentrations relevant? Are these hugely amount larger than anything you would find in a sample? And in fact, they are relevant. Turns out the concentrations that these folks put into the milk are fairly high. And the reason why is this: if they adulterate this milk with very small amounts of melamine, they're not gaining very much. They're gaining very little because they need to, for example, dilute the milk by 10%, then they need to add 10% more protein-like substance, right? So melamine. And so it turns out they put in about typically 1 millimolar melamine in there, something on that order. Typically, you would almost never find 0.1 millimolar of any of these adulterants in any of this. This is sort of just to show off that we can actually detect much lower than you would typically find. And so next, we repeated the same sample preparation method with 4 other potential adulterants. It might be hard, but for those that can see these schematics, they look very similar to melamine. They're basically, you can think of them as melamine derivatives. And for these substances, and these are also similar in structure, they're not melamine derivatives, but they also have nitrogen, highly nitrogen-rich molecules, small molecules, that are, again, very widely available to these folks to do adulteration. So for these, we're also similarly able to detect similar concentrations of these species directly in milk. So in summary, we're able to detect 5 different potential milk adulterants from whole milk in a portable system using the simple sample preparation method and SIRS, simple SIRS chips. Thank you very much for listening.
Thank you very much for a really enjoyable presentation. What we'd like to do now is open up the floor to questions that people might have regarding the presentation for our presenter.
Do I need a mic or?
No, just big voice.
Okay. I'm wondering why the choice of the trichloroacetic acid, and specifically, is there a reason?
Sure. It's a well-known protein precipitant.
Okay.
Yeah.
Is the sensor reusable?
No, it's a single use. Single use.
Could you talk a little bit more in detail about the sensor, the pricing, and how is it a viable, internationally, where the dollar is quite expensive?
Right.
How, what might be, is it in operation yet? Is it just a test? I'm just curious to know more about it.
Right. So right now, this is fairly in R&D. We believe that we can make this compatible with particle-based SIRS. The fabrication of this is fairly inexpensive. This is as much as I can tell you. Materials-wise, it's not expensive, and equipment-wise, it's something that we can do, and we believe that we can produce fairly inexpensively.
You mentioned doing nano-ink printing, and you mentioned that the surface tension of the milk itself versus the...
So it's the other solution, the cleaned-up solution.
Could you, Victor, could you please repeat the question?
Oh yeah, definitely. So the question was the surface tension of the milk itself. Does that close the nanofingers? Is that correct?
Yeah.
Yeah. So it's the cleaned up solution of the milk that's drying out. So it's mostly aqueous solution that has the small particles that's found in the milk. Small, not particles, but small molecules.
So what I'm getting at is the material that you are using is therefore a flexible material?
Yes, it's a polymer. It's a flexible polymer. Yes.
When you do the precipitation procedure, basically you can precipitate all the proteins contained in the milk.
Yeah.
But then I'm just surprised that then you can see very clear signal of just your molecule of interest, and you don't have any like other signals coming, for example, for carbohydrates present in the milk or other smaller molecules that are still in the milk.
Right, so it's a very good question, and the question was that once we precipitate out the proteins, there are still small molecules that are left in the milk. And so why don't you see spectra from those molecules? Basically, we get lucky, and in two ways. A lot of those molecules do not have a lot of nitrogen groups, so they do not bind as strongly to the gold. Two, they're much lower concentrations. They happen to be in much lower concentrations than these adulterants. And three, that they have weaker surge response. Not all molecules have the same surge response. Some molecules with particular groups, like these aromatic compounds, have much stronger responses than, for example, aliphatic molecules. That some of these molecules, smaller molecules that are found in milk, are.
Victor, we've got a really patient person.
Yes.
So my question is, so this is in raw cow's milk,
Yes.
but infant formula is typically dried. How do
Yes.
these sensors work with dried infant formula, which is often used anyways because it's cheaper to ship and all these sort of things?
Yeah. So you basically have to prepare the formula like you would prepare it for an infant, basically make it in liquid state. Yeah. So we're working on it. That's something to try. Because these things, it should work. It's something to try. Yes.
Have you explored other applications with the sensor?
Yeah, so we have out of the things that are published that I can tell you about, there's some pesticides detection. For example, there has been demonstrations of detecting pesticides with this sensor, and I believe that's as much as been published. But definitely us in the lab.
Very interesting chemical study. It seems to be a batch process. How I can use in a very automated environment of large volume, one. Second thing is, why do you need all these columns? Gold itself is if you make it a colloidal particle,
Yes.
it will very well absorb. It has a very surface activity for the amino compound. I'm not a chemist, I'm an electrical engineer, but the way I know a little bit of knowledge, maybe you can highlight why and how.
Yes, that's a good question, right? So we do rely on the gold to absorb the amino compounds, but as you know, the proteins in the milk contains quite a bit of also amino groups, and so if you do not remove them, they will absorb to the sensor. And as you saw in this plot, for example, or this plot even more so, that they will block significantly this signal. And your first question is, how do you make this automated? Well, the answer is microfluidics. So we're working on that. I don't have something to present to today, but it definitely, you're absolutely right, it is necessary, and we're certainly working on it.
So as you rely on the binding of the amines from melamine to the gold,
Yes.
have you tried to mix with other molecules that have a stronger binding affinity to the gold to see if actually you can trick your sensor?
For example, yes. For example, if you use styles, they have stronger binding to gold. The sensor will pick it up, but you can't. You have a hard time tricking the sensor because they will have a different spectrum. So they will have, for example, a peak somewhere here and not here because it's a different compound. And so you will bind it, you will exclude melanin, for example, from binding, but you will know you have something else that's interfering that might be actually quite bad for you, and you want to detect it.
But is it at the same concentration?
It might be, yeah. So depends how strongly the affinity is. That species might be in a much lower concentration, and it might be able to interfere, and you might still be able to detect it.
So we have a unique problem in India. It's a very agricultural economy, lot of milk production, lot of yogurt production, and lot of ghee production, those shortening. The whole thing relies on amount of fat content in the milk. So people have devised very clever schemes of removing the fat and adding something else to make up the fat content, so to make it up. Is there anything here from a layman's point of view? Is there anything here that can be used for such a check on original versus not?
Original versus not is a little bit hard because there's, as you described, there's many creative schemes of removing fat and putting it back in. And depending on the scheme is, you have to think about it, how to actually go about detection. There probably might be a way of going about it, but I just don't know enough about those schemes to tell you right off the bat.
What can you tell us about the dynamic response of the sensor? What I'm thinking is, the amines may bind to the gold, and then if you were to reduce the concentration, they may reversibly unbind and then back. And so if the sensor were able to kind of follow ups and downs, you might put it in line in some application where you could see things varying. Have you looked at anything like that?
Yeah, so not me personally, but many other groups, in addition to our group, have looked at using SIRS as a dynamic sensor. Now, with this particular sensor, that's a little bit hard to do because this relies on closing the fingers, and that closing of the fingers creates these regions of high electric field and produces this enhancement. Other folks that rely on particles that are pre-closed, pre-aggregated, for example, or we have looked at having the pre-closed fingers interact in solution and allowing these molecules to bind and then flushing a clear solution and allowing them to unbind. It is possible, and people have done this, but there are some challenges that are involved in this. But it is being done.
What's the wavelength?
What's the wavelength? So the typical wavelength that we excite this is 785, and the shift in wavelength is not tens of nanometers.
How did you arrive at 5 figures instead of 3, 6, 7?
Yeah, there is, and it's a very good question. And let me try to go back. So what you're trying to do is that, first of all, you're trying to make this asymmetric structure, and there's only certain structures. If you, for example, have 2 fingers, there is a plane of symmetry, and when you're exciting it with electric field, you don't know how, you don't want to try to orient the sensor to the laser. You want to allow this, the laser to kind of hit the sensor willy-nilly, because it makes design of the rest of the equipment much easier. So with a structure that's symmetric, you have to have the laser, so the electric field, be aligned to the sensor. And that if it's off axis, the alignment is not there, you will not hit the dipole of virtually this antenna structure, and so you will not get a very high enhancements. So for example, 2 or 4 don't work as well. 3 works pretty well because there's more symmetry, and sort of 5 is as high as you'd go without having these structures being awfully complex. And so 5 works pretty well. So, but this is a very good question.
If you combine the adulterating compounds, how does your signal? Is it a linear combination, or is you get interferences?
It's a very good question. So when they're dilute, when they're fairly dilute, and the sites of no gold do not interact with each other, they're a linear combination. you can simply, if you know the spectrum that you're looking for, you can subtract it off. There are some weights to this linear combination. The weights are how strongly this compound has surrounded the response of each of as a function of the wavelength. But when it's dilute, when it's not dilute, and there is actual competition of sites, and sites where one molecule will bind and another species, another adulterant will bind, they're close enough to interact, you will have shifts in spectrum and be very, very nonlinear and hard to tell apart.
Pick me. I have a question.
All right.
This is sort of a kindergarten question, but it relates to the slide that you've got. I think I get how normal Raman works, photon molecule interaction. There's something really special here that gets you 10 to the 4 enhanced, which is a surface enhanced effect. Could you give us a simple physical picture of what happens on the gold surface that creates these really high electric fields?
Sure. Well, it's basically the same thing roughly happens in an antenna, just in different frequencies. Basically, you take your laser, and the laser has an electric field, and it excites the surface of the material, the surface of the gold, right? So it excites the surface of the gold. And now that, you basically now you could concentrate the electric field in a very small area, and just as in an antenna you have very high oscillations, because when you do this, you're hitting this laser, you choose this laser wavelength to be at the resonant frequency of this plasma, basically these electrons at the surface of the gold. So you hit it at the resonant frequency, right? And this molecule changes this electric field a little bit by robbing, a certain amount of energy out of it. So it shifts the wavelength or the frequency of the electric field. And so when now these oscillating, these very powerful oscillations of these electrons at the surface occur because oscillations of electrons generate a traveling electric field. You propagate now, the electric field that you propagate now is now enhanced by this antenna structure. So it works fairly similar to an antenna, just at a different frequency.
So the molecule, in a sense, you're almost pumping the molecule to get higher energy out.
So the molecule basically sort of alters the field that you put in, yeah. This is sort of a modulator. You can think of it as a modulator.
It looks like there's one more question, or two more.
Modulator as an inelastic scatter.
Inelastic scatter, exactly.
More than a modulator.
Yeah, exactly.
So once you have these being spit out of the production factory, next to nothing,
sure,
and millions of them are out there,
yes,
have you considered the waste stream? Gold, even in small amounts, can be relatively valuable and relatively rare.
Yes.
And it may be worth reclaiming, and it might even pay for the reclamation, but have you given any thought to that?
Yeah, no, we're not me personally, there are folks who are thinking about this on our team, but it's something, kind of in the future, something to think about, definitely. This is a very good question. And also the environmental impact, right, of the sensors being up there, yeah.
So it was a really nice presentation, thank you. So my question is related, like you said, it depends on the drying of the milk or the milk product that's left. So how much time does it take to dry it? What conditions do you need? Like, are there any specific conditions that you focus on? And then what is the efficiency of all the fingers coming together?
Yes, just to repeat the question, first of all, the efficiency of the fingers coming together, what's the efficiency of this process of closing the fingers? And the second question is, how quickly does the drying happen? Is there anything you can do to accelerate it, or anything we do? So the first question is, I guess, the efficiency of the closing together. They close together pretty well, as you see. On the next slide, this is actually very representative. It's not sort of the best scenario picture, although it is the best scenario, but if you look across the sensor, they all look like this. The efficiency is great. It's a very robust process. To accelerate it, and normally, depending on the liquid, if you put ethanol in your solution, it makes it evaporate quicker, a few minutes. You can heat it. You can blow nitrogen over it, for example, sort of a simple like office sprayer would also work. You can quickly dry it off, and it will also produce these very nice finger arrangements. So you can close them fairly quickly. There's another question.
I was just wondering, you just use spherical gold nanoparticles to put on your sensors?
What was that?
Your nanoparticles, just normal spherical nanoparticles?
Yes. What about them?
Because like on the previous slide, I thought that some of the nanoparticles look kind of spiky, and I know somebody used kind of
Spiky. Yeah, folks also use normal spherical particles because the idea is that in the gaps of the particles, what you're trying to go is for regions where electric field is high. And for example, when two spherical particles come together, there's that narrow gap, and that also produces good surge. Yeah.
Folks, I think I'm going to hold off questions at this point because we need to respect TI auditorium schedule and the fact that Vince, our AV guy, has to check out at 1 o'clock. But the presenter will be here, so if you have more questions, please come up here and engage with him directly. And let's give Victor a round of applause.